This is Calculus 2, Section 1. Um, so if you're using Larson Calculus, this is Chapter 7. 7.1 is area of a region between two curves. So back in Calc 1, you should have talked about what integrals represent graphically, and that would be the area under a curve. And now in Calc 2, we want to know how do we find the area of something bounded by functions. So if we have two functions f and g, and they both lie above the x-axis, and g lies below f in some interval, we can find the area of the region between f and g in that interval. So we're saying we have already drawn two functions. The green is f, the red is g. In some interval where g is below f, we want to find the area of that region. So here I'm talking, don't know why that's it. Okay. So here I am talking about this region in here. How do I find the area of that? Well, so we're talking about the area between f and g. That's going to be equal to, I would take the area under the green, which is all of this purple. So you would take the area under F and we're going to subtract this area out that's below G. So we take the area under F minus the area under G, and that gives me just the orange region. So if you recall Riemann sums from Calc 1, you can partition A to B into n subintervals of width delta x. So I can draw in a representative rectangle right here. So I sketch a representative rectangle. And this is going to be, we're going to have a point x sub I. In that interval, the width of that rectangle we call delta x. The height of that rectangle is going to be that function value of f at that value minus the function value of g at that value, right? Because it's f minus g. That gives us the height of that rectangle. If you want to know the area of one representative rectangle, you would take the height minus, or sorry, the height times the width. And again, that is area of one representative rectangle. and the area of the whole uh, interval, we could take the limit as n goes to infinity of the summation from I equals 1 to n of that area. So this is the total area. That leads us down to our definition in the box. If f and g are continuous functions on an interval a to b, and g of x is less than f of x for all x, and the interval, then the area of the region bounded by the graphs and their vertical lines, the interval, is going to be area is equal to the integral of a to b. It's going to be f of x minus g of x dx. Now that's a generic formula. We can also find area with respect to y, but we will talk about that on the next page. So just a couple of notes. You do not need f and g to be above the x-axis for this to work, because no matter where you're at, f of x minus g of x, that top minus the bottom function, still gives you the height of the rectangle. Sometimes area will be bounded by two curves that intersect at two or more points, and you would need to calculate integration limits, and you may have multiple integrals. Okay, like I said just a couple seconds ago, we can also apply this concept with horizontal rectangles and integrate with respect to y instead of x. So if you're using vertical rectangles, your area is going to be from one x value to another, and you're thinking top minus bottom dx. If you're horizontals, if you can draw them, sorry, if you're rectangles, you can draw them horizontally. Your area becomes one y value to another, and then you're thinking right function minus left, and this would be dy. So let me just draw an illustration for these. We already saw like let's make the red down here and the green go up like there. So you already saw an example of that. If your rectangle's in here, you would do top minus bottom. Example of horizontal would be functions that are like that and like that. And then your rectangle would be like this. And you would go from this right function minus the left. So integration is an accumulation process. So we go from like a known pre-calc formula, which would be like the area of a rectangle. We then have a representative element. And then the accumulation of these elements becomes integration. Okay, now for some examples. We want to write a definite integral that represents the area of the region. So we're given two functions, y1 and y2. Sometimes you're given the graph, sometimes you're not. Um, when you're not given a graph, it's when your college algebra, trig, skills come into play from when you graphed functions. So you should know how to graph those. But we are given a graph in this one. So let me start by pretending we didn't have a graph. How would you know your integration limits? Or, in other words, where the functions intersect? So anytime you're given functions and you may not know the graph, you want to find intersection points. That is where you set the one function equal to the other. And we solve for x, subtract 2x, those cancel. Subtract 5, you would have x squared minus 4 equals 0. You can either add 4 to the other side, take the square root, or you can recognize this is a difference of squares, where you have x plus 2, x minus 2 equal to 0. If you factor, x is equal to negative 2 and positive 2. These are your limits of integration, which you could also see over here from the graph at 2 and negative 2. But you're not always given a graph, so it's good to practice solving for them. So our area we know is going from negative 2 to 2. Um, so we need to determine our top minus bottom. So if you drew in a rectangle, the top function is this line, which is the 2x plus 5. The bottom function is that parabola, which is the x squared plus 2x plus 1. So we're going to go top minus the bottom, and that's dx. Okay, we can simplify a little. We'll have negative 2 to 2, 2x plus 5 minus x squared minus 2x minus 1 dx. Positive 2x, negative 2x cancel. We're going to have the integral of negative 2 to 2, negative x squared plus 4 dx. All it wanted us to do was write the integral, so you would be done. Also, whenever you're solving problems, make sure, let's go back to the picture real quick. Wherever you draw a rectangle, make sure that the top minus the bottom is always that line minus the parabola. There are in some cases, which we will see in an example coming up, where the top minus the bottom or the right minus the left are not always the same. But we will talk about how to do that coming up soon. Okay, let's move on to number 14. Sketch the graph of each function and shade the region whose area is represented by the integral. Okay, since these are in terms of y, I automatically know this is some type of right minus left. When they're in terms of y, your function is x equals whatever's in your integral. So starting with this, I'm going to say x is equal to 2 square root of y. My next function, x is equal to y. It's not negative y because that minus is in the formula. Okay, to help me graph, I want to make sure these are y equals. So the only one we really need to do anything with is this purple one. Divide by 2 and square both sides. So you get x squared over 4 is equal to y. And I just write this as 1/4 x squared. I know that's a parabola. And I know x has to be greater than or equal to 0. From the original equation. So let's get a sketch in here. I know my y values. So this 0 and 4, those are y values. So we're going from 0 to 4 on the y-axis. So I'm just going to make a table for my purple function. Um, we know y is going from 0 to 4. So when y is 0, x is 0. You would just plug them in right here, those y values. When y is 1, the square root of 1 is 1. 2 times 1 is 2. I'm going to skip 2 and 3 because they're not perfect squares. Square root of 4 is 2. 2 times 2 is 4. So we should be at 0, 0, 1, or sorry, 2, 1, 4, 4. So it's looks something like that. X equals y, that's just your normal straight line. And we're shading that region whose area is represented. So that's all of this. It is okay if you kept plotting values and said this is a parabola that goes forever. And it's okay if you extended this line to go like that. However, we're only caring about the limits given to us, the 0 and 4. So the shaded region would just be all of this. Okay. Here's one, which we'll see in a second. When I was talking about, you have to make sure that your rectangles are always the same functions, whether it's top minus bottom, right minus left, the whole way. So we want to find the area of the region by integrating with respect to x and integrating with respect to y. So first thing first, just in case, whether it's hard to see on the graph or you're not given the graph, let's go ahead and find our intersection point. And that would be setting x squared equal to 6 minus x. It's quadratic, so we get everything to one side, set equal to 0. Okay, we need two numbers that multiply to -6 and add to +1. My factors of 6 are here. The ones that make a +1 would be -2 and +3. So we have x's -2 plus 3 equals 0. So that tells me x is equal to 2 and -3. Okay, if we take rectangles and draw them, no matter where we go, top minus bottom is always this line minus the parabola. So with respect to x is fairly simple. Area is equal to the integral of -3 to +2, right? -3 to +2. Those are the integration limits we found. And we said the top is the line, which is that 6 minus x minus the parabola dx. Okay, we have the integral -3 to 2. Just distribute that negative and take the integral. 6x minus 1/2 x squared minus 1/3 x cubed. Evaluating from -3 to 2. You would get, plug in the 2, you would have 12 minus 2 minus 8/3 minus, plug in the -3, you get -18 minus 9/2 plus 9. Simplifying all of that, you get 125/6. Okay. Again, so we plugged in the 2, you get all of this. Minus, plug in the -3, is all of this. And then you just simplify. Okay, taking a look at respect to y. Okay, when you do respect to y, first of all, you need y coordinates for integration limits, and your functions have to be in terms of y. So, for part B, solving this for x, x is equal to square root of y, and x is equal to negative square root of y. That negative square root of y is the left side of the parabola. That positive square root of y is the right side of the parabola. Let's find a different color here. This x equals 6 minus y is the line. Why I made them 3 different colors, you will see. Okay, integrating with respect to y. Let's look here. If you draw in rectangles, if we draw a rectangle there, we draw a rectangle there, we draw a rectangle there, whatever. Okay, here's my problem. Right here, that rectangle, the right is the green parabola, the left is the blue. Okay, moving up here, we have this rectangle. The right is the line, the left is the parabola. So it's not always line minus parabola or parabola minus parabola. So this is one where we have to, did not want to do that, split right here at 4 because that's where it changes from either line minus parabola or parabola minus parabola. So we are splitting at y equals 4 because that's where the change is. Okay, so area equals, also we need y values, so plug in -3. For x, you get 9. For y, and 2, 4. So worried about the y values now. The first area we're going to find down here is going to be from 0 to 4. And that's going to be that right parabola minus the left. And that's dy. Then our second integral up here is going from 4 to 9. And it's now going to be the line, which was that 6 minus y, minus the left side of the parabola. And it's dy. Okay, now we can simplify. So we're going 0 to 4. This just turns into 2 radical y dy, because these two make a plus, plus the integral of 4 to 9, and it's going to be 6 minus y plus square root of y dy. Okay, I'm just going to rewrite these as 2y to the 1/2 plus, we're going to have 6 minus y plus y to the 1/2. Okay, now we can take the integral. So for that first one, we would have 4/3 y to the 3/2 evaluated from 0 to 4 plus we'll have 6y minus 1/2 y squared plus 2/3 y to the 3/2. And that one's evaluated from 4 to 9. Okay, the first one you would get 32/3 minus 0 plus, we're going to have 54 minus 81/2 plus 54/3. So when you plug in the 9, minus 24 minus 8 plus 16/3. Okay. So all of this was from here, and all of this evaluating was all of that. Okay, simplifying everything, if you put all that in the calculator, you get 125/6. So either way you do it, you get the same result, but part B is more complicated because you have to split into two separate integrals instead of just having one. So which way is simpler? I would say respect to x because only one integral is needed and you're not splitting it into multiple ones. Or if you're someone that likes to do math and write it all out, maybe you would say part B is simpler. Okay, we're gonna move on to, we just have two more examples. Then the next video we will start covering volume. There's two sections over volume. One's called a disk method, one's called the shell method. Okay, sketch the region bounded by the graphs of the equations and find the area of the region. So we're not given graphs, but we're given functions. So my first thought would be to start with intersection points by setting 2y minus y squared equal to negative y. So I'm going to have negative y squared plus 3y equals 0. Factor out a negative y. So y is equal to 0 and 3. Okay, let's sketch. We know we're only going from 0 to 3 on the y-axis. I'm going to sketch this one in red. I will sketch this one in blue. Remember when they're in terms of y, they're like x equals. So it's like x equals 2y minus y squared and x equals negative y. If you solve this one for y equals negative x, that's a straight line with a slope of negative 1. So look something like that. The red one, we can plug in y values to get the x. So if you plugged in 0, x would be 0. If you plugged in, let's see, if we plugged in 1 for y, 2 times 1 is 1, minus 1 is 1. So we're at 1, 1. We plugged in 2 for y, you get 0 for x. We plug in 3 for y, you'd be at 3, you'd be negative 3, 3. So this graph is something like that. Find the area of the region. So the region we're looking at is in here. We found our limits of integration there. So we know area is equal to 0 to 3. Since its y values are rectangles, we know are going to be horizontal. And no matter where we draw them, it's always going to be that red minus the blue. So it's going to be 2y minus y squared minus negative y dy. So 2y minus y squared plus y dy was 0 to 3 negative y squared plus 3y dy. Integrating, you get negative 1/3 y cubed plus 3 halves y squared, evaluating from 0 to 3. You're going to end up with 27 over 2 minus 9 minus 0. And that's going to give you an area of 9/2. Okay. And the last one we have is graphing trig functions, everyone's favorite. So we have f of x is equal to sine x, g of x is equal to cosine 2x. Here we're given bounds to go by. When you're given bounds like this, those are going to be your integration limits. So we are going to sketch, just in case you don't know which one would be on the top or the bottom. I'm going to count by pi over 6. So 1 pi over 6, 2 pi over 6, 3 pi over 6 would be pi over 2. So this would be at negative pi over 2. And we're at pi over 6. Okay, so let's start with sine x. Going to be at negative 1 at negative pi over 2. Somewhere between here is at 0. Then it goes, sorry, um, sine x would be down here at negative pi over 6, somewhere down here. Then it's going to be at 0. So my sine is something like that. Okay, my cosine of 2x, that has a period of pi. But if I'm just going between this interval, you can just plug in numbers. But at negative pi over 2, it's going to be at negative 1. It's going to hit 0 between negative pi over 6 and negative pi over 3. We're going to be up at 1 and then here. So the cosine looks something like that. The region they're bounded by is in here. So really the graphing was to see which one's on top, which one's on bottom. And we can draw in vertical rectangles. And no matter where we place a vertical rectangle, it's always the blue minus the red. So we are going from negative pi over 2 to pi over 6. Cosine 2x minus sine of x dx. Integrating, you get 1/2. Sorry, don't need the integral. Integrating, you get 1/2 sine of 2x plus cosine of x. Evaluate from negative pi over 2 to pi over 6. Plugging in your pi over 6. You would have 1/2 times rad 3 over 2 plus rad 3 over 2 minus 1/2 times 0 plus 0. So that's rad 3 over 4 plus radical 3 over 2. We'll have common denominator and combining, you get 3 rad 3 over 4. And that would be the area bounded by those two functions on the interval. That is all for the first section.